All right, so today I'm going to work three example problems from the rotational motion worksheet, which you should have. I should have given you a copy of this the other day. The three that I'm going to work the example of, I'm going to work number 3, work number 5 and number 6. Number 5 and number 6 are kind of related to each other, but I think it's a good kind of subset of the sorts of problems that you will see as you work through the problem set. Okay, so over here, I will put down the times that you can expect to see these particular problems worked, so that if you want to go back, at some future time and watch this video, you may. Okay, so let's go over here where I have prepared these three problems. Okay, so the first one is right here. Okay, so this is number 3. Okay, a centrifuge in a medical laboratory is rotating at an angular speed of 3,600 revolutions per minute. Okay, so this is the first number that we have to deal with. This is 3,600 revolutions per minute. It can be challenging when you're beginning working on these sorts of problems to, understand what these different variables are. Now, I want to remind you, you've got this sheet somewhere, at least I hope you do. You should probably even have it out. With all the variables and their names on it. So I want to just kind of remind you real quick that basically what we've got here, and this is the mapping between the linear and the angular, right? So displacement, linear looks like this, and angular looks like this, right? This particular thing is measured we typically want our angles to be in degrees, but in this particular case, we're going to be in radians, right? Now, a non-preferred unit would be revolutions/rotations, which are exactly the same thing. Okay, so just be aware of that, okay? Then we've got velocities, and velocities tangential, that is. Tangential just means it is, kind of along the edge of a circle. And the tangential velocities map to omega. Okay, now omega, we're going to draw it like a W. It's just kind of a rounded W. And remember, that is going to be in preferred units, that will be radians per second. Sometimes you will get it as any of these things on the top. So it can be degrees, radians, revolutions, or rotations on the top. And on the bottom, any sort of time unit will work. And then we've got an acceleration, a tangential acceleration, and that goes to an angular acceleration. Okay, an angular acceleration in preferred units, that's radians per second, okay? And again, anything on the top, degrees, radians, revolutions, rotations on the top, and on the bottom, I've never seen it as like radians per minute squared, but I've certainly seen like RPM, which would be rotations per minute per second. I've seen things like that, okay? So just to be aware, okay? So when I see something like revolutions per minute, okay, I'm immediately thinking, oh, look, this is a change in angle, and this is a time, okay? So that, if I look over here, we've got a change in angle over a time, so that is a rotational velocity. Okay, so a centrifuge in a medical laboratory is rotating at an angular speed of 3,600 revolutions per minute. So I'm going to go ahead and make that my initial angular velocity is 3,600 revolutions per minute. Okay, now remember, a revolution and rotation are exactly the same thing. Also remember that we don't particularly like revolutions or rotations. They're going to make our lives a lot more unpleasant, so we're going to have to convert that before we begin. Okay, when switched off, it rotates 50 times. Okay, 50 times. And that's a really annoying thing because it doesn't really have a unit. However, it kind of does because it says it's 50 rotations. Okay, so if we've got rotations, we're dealing with this delta theta right here. So we know that delta theta is 50 rotations. 50 rotations. Okay, again, we don't like rotations. We don't like revolutions. We like radians, right? So we're going to have to convert all that before coming to a rest. Okay, so its final velocity is going to be 0. Its final angular velocity. Now, to be clear, its tangential velocity will also be 0. Its linear velocity will also be 0. But it looks like because they're giving us all these variables in angular form, we're going to need to do this in angular. Okay, find the constant angular deceleration. Now, that's annoying. angular deceleration. So they want the angular acceleration. So here's our givens. And our required, we're going to want this, right? We want our angular deceleration. Now that is the alpha symbol. You guys, for the most part, will call that fish. Whatever. All right, so here we go. We've got, I'm going to go ahead and convert these units, okay, using, you guys call it dimensional analysis. I think dimensional analysis is a lot bigger than this. When I learned this was called the factor label method. It doesn't really matter. So what we're going to do is we're going to multiply by a bunch of fractions, which equal 1. So right here, I want to get rid of this revolutions, and I want to turn it, let's zoom in a little bit. I want to turn those revolutions into radians, okay? So 1 revolution equals 2 pi radians. Okay, cool, so now we got our radians. And I want to get rid of these minutes on the bottom, so I'll multiply by 1 minute over 60 seconds. Okay, noting that this quantity equals 1 because all those things are the same, this quantity equals 1. Okay, so if I multiply this, 3,600 revolutions per minute, I'm going to get 120 pi rad per second, right? Because the minutes cancel out, the revolutions cancel out, and I'm left with rads per second. Now, note I could have written that instead of as 120 pi. I could have multiplied that in my calculator and gotten, some much bigger number, or not bigger, but the number with a whole bunch of decimals. I don't want to carry the decimals around. I don't want to deal with it, so I'm just going to leave it as pi for now. Okay, so for the delta theta, I've got 50 rotations. So I'm going to use 1 rotation is 2 pi rad. Okay, notice here, I think this is important to note, that what's going on here show that a rotation and a rad are exactly the same thing. A rotation and a revolution are exactly the same thing. All right, so if I multiply that out, I'm going to get 100 pi radians. Okay, again, I could have plugged in 3.1415, whatever pi is. Then I'm carrying a bunch of decimals around. I don't feel like dealing with it. Okay, so now I've got an initial velocity, I've got a final velocity, and I've got a displacement, and I'm looking for an acceleration. Okay, so let's see. Let's see what equation has initial velocity, final velocity, and a displacement and an acceleration. Okay, so if I'm over here on this particular sheet, let's look around. Okay, so on this, so I'm looking here, right? I guess I might as well, I don't want to look at the limit equations. We never use those, right? So let's zoom in. Let's see. So like right here, I've got an initial and a final, but, I'm not really looking for that. So that's not really a great equation. Let's see. On the average acceleration, well, that's what we're looking for. We're looking for the deceleration. The change in omega we've got, but we don't have the time. So that's not really going to help us very much, right? So we've got this. So let's go down here to these 3. Right, so we've got that. This is what we're looking for, so that's cool, but we don't have that. So that leaves us 2 unknowns, right? Let's see here, delta theta. Well, we don't know. Wait, we do have that. We have this. We don't have time. We're looking for this, but we don't have time, right? So there's 2 unknowns in that one, so that's no good. So we go down here to this bottom one. Let's see here. We've got a final. We've got an initial. This is what we're looking for, right? And we know that. So this is the equation that we're going to use. Okay, as it seems that we always use this equation if we don't have time, right? I mean, it's not always, but it's a pretty good general rule. Okay, so let's go ahead and let's go up here and let's solve this sucker, right? So let's go right in here and let's do our solution. So our solution, let me go back to white. It pops a little better on the black background. So our solution is going to be, I'll try to keep this in omega squared equals omega naught squared plus 2 alpha delta theta. Okay, so we need to solve for alpha. So let's go ahead and do the algebra there. So alpha then equals omega squared minus omega naught squared divided by 2 delta theta. Okay, that's fairly quick, but I think if you walk through the steps, you will get that exact same answer, okay? So let's go down here and let's go ahead and plug in chug. let's see here, alpha equals, okay, so we end up at 0 movement, but we were going 120 pi radians per second squared. Okay, and now we're going to divide all of that by 2 times 50 revolutions, which was 100 pi radians. Okay, so plug and chug, keep going. Alpha equals negative 226.19 radians per second squared. Okay, so then the question here becomes, sig figs. So if we go back up here and we look at the problem, let's see, we've got 3 right here. Oh, we've only got 2 right there, so that's problematic. Okay, or maybe problematic is the wrong word, so we only have 2 sig figs in our final solution here. Because what's going to end up happening is we're going to only end up having 2 right there, right? So such is life. So we're going to end up with 2 sig figs, and so alpha equals negative 230 radians per second squared. Now I think if you look at the key, so if we go over here, this particular key down here, this particular key I believe kind of ignored the sig figs. I don't remember where I got all these problems. I compiled them last year. But for whatever reason, this is going to ignore sig figs. You'll also see that these particular problems up here, a lot of them just don't even have anything to do with sig figs in them, right? So anyway, doesn't matter. Okay, so, anyway, so these answers will be correct. They just won't necessarily be correct with sig figs. Okay, so let's go down here. We'll go down to number 5. Okay, a race car. Oh, I love these problems. Okay, so a race car is traveling around a circular track of radius 200 meters. So here's our circular track. Okay, let's give it a radius somewhere here. Dadgummit. Okay, let's let's create that like that's the center of this sucker, all right? Give it a nice radius here. Okay, that radius is 200 meters. If the car moves with a constant speed of 80 meters per second, so it's here, and it's going 80 meters per second. A, find its angular velocity. So here's our given, right? What's our required? We need an angular velocity. Okay, angular velocity equals what? And then it's tangential acceleration. Okay, so it's tangential acceleration. So that's going to be A sub t equals what? All right, now before I move on to this, I want to kind of mention here how I knew that this one right here was going to be a angular. It said velocity, but I wrote it as an omega and not as a v. Okay, and then it said acceleration, and I wrote it like this, and I did not write it like that. Okay, so those were the options, right? I could have written it in different ways. Okay, I suppose here I also could have written it as a sub c, okay, because there's lots of different accelerations here. And so what I want to point out, there's some very important words here. One, angular velocity. As soon as you see that word angular velocity, you know that it has to be omega, right? Angular means delta theta, it means omega, or it means alpha, right? So as soon as you see the word angular, it has to be that if it's angular displacement, this if it's angular velocity, which it is, and this if it's angular acceleration, okay? Now when it says acceleration, okay, in this case we don't have the word angular, okay, is not there, so it cannot be the fish or the alpha. Okay, now it says tangential, so that means it has to have a little t by it, okay? If it had a little c by it, it would be centripetal, okay? So centripetal would mean towards the center. Okay, so now that we've kind of gotten through, the symbols and kind of what it is that we're working on, what we're working with, okay, let's talk about how to solve for these. Okay, so the angular velocity here, omega, is right here. Now this particular thing over here, this is a velocity, right? So this 80 is a velocity, okay? And the key is I want you to note that it is moving tangential to this circle, okay? So this is the tangential velocity. Okay, so if you have the tangential velocity, remember, anytime you're working between the tangential anything, okay, tangential anything, tangential, that could be displacement, that could be velocity, and that could mean acceleration. And you're trying to go to or from the angular version of the same thing, angular version of displacement, velocity, or acceleration, right? So symbolically, that would be delta theta. Velocity would be v, or not v, sorry, omega. And acceleration would be alpha. And these would normally be delta x. Velocity is v sub t because it's tangential. And the acceleration would be a sub t. Okay, so anytime you're going from one of these to one of those, you just have to multiply or divide by r. Okay, and it's that straightforward, okay? So the question is which one? So we're going from v sub t to omega, and that's what this equation sheet is for. So right up here in the middle, let's see which one we're going to use. We got v sub t equals r omega. Okay, so basically if you have the angular quantity, you multiply times r, and that'll give you the linear quantity. Okay, so let's do that. Okay, so in other words, our equation looks like this. Okay, so v sub t equals r omega. Okay, so I'm looking for omega here, so we'll solve for that. So omega equals v sub t over r. Okay, that's our solution, and then we'll plug in numbers. I think I'll just pause while I plug in the numbers. All right, so I just plugged in the numbers. So the velocity is 80 meters per second divided by the radius of 200. And notice we get 0.40 per second. Now, there's a moment here where you're thinking, okay, Wagner expects me at the end of each problem to check my units and to check my sig figs. Okay, so the units here, the meters cancel, and we're left with per second. Now, this would be an error to leave it like that. Remember, a radian is a unitless unit. So there are times, like right now, where there's no unit there, and I have to know that there has to be a unit there, okay? And it wouldn't be entirely wrong to say per second, but I'm going to require you to put the word radians there. And you're going to have to know that because this is an omega, and omega is radians per second, okay? As far as sig figs are concerned, let's see, we've got 200, so I've got 3 right here, and I've got 3 right here, so I'm going to need 3 in my answer. So a little bit annoying, I didn't leave myself space for it. We're going to squeeze in another 0. Okay, so this is 0.40 radians per second. Okay, cool. What was the B part to this problem? The B part to this problem, find its angular velocity and its tangential acceleration. Okay, so I need a sub t. Okay, and I chose this problem because we haven't really talked about this particular. It's tangential acceleration. So it's tangential acceleration. Well, here's a key here. Okay, we've got v sub t is 80 meters per second. Right over here, v sub t is 80 meters per second, and over here, v sub t, 80 meters per second, okay? So in other words, its speed is not changing, its tangential velocity is not changing. So if this tangential velocity is not changing, then its tangential acceleration is 0. That one is just a logic question, okay? So if you're not speeding up, your tangential velocity is 0. Now you still have a centripetal acceleration because you are turning towards the center. Okay, so there is a centripetal acceleration. At all times you are turning towards the center because if you were not, you would keep going straight. Okay, that does not equal 0, and we will talk about that some other time. All right, let's go down here. The race car in the last problem increases its speed at a constant linear acceleration from 80 to 90. Okay, and that takes 10 seconds to go from 80 to 95 meters per second. Find the constant angular acceleration and the angle the car moves through in this time. Okay, so I've drawn the radius here, and I've shown it, moving at 80 meters per second and then 95 meters per second. And what I want to know is while it does that, okay, so here's my delta theta, right? That's the angle the car moves through during this time. And the angular acceleration. So one of the things I'm going to be looking for is delta theta. And the other thing that I'm going to be looking for is an angular acceleration. So that's going to be an alpha, okay? Let's see. This is kind of an interesting way to do this. Let's just do this more formally. So given, I know Vt naught, its initial tangential velocity is 80 meters per second. I know its v sub t, so that's its final tangential velocity, is 95 meters per second. I know r is 200 meters, 200.0. Is there 0.0? Is it just 200? Oh, it was just 200 from earlier, right? But it had a decimal on it. Here, let me get rid of that. Let me get rid of that here, too. Okay. All right. And I know the time is 10 seconds, right? 10 point seconds. Okay, noticing that the time has 2 sig figs, everything else has 3. So that's going to screw up our sig figs, I guess. Okay, so I have 2 things that I'm looking for. One, I'm looking for the delta theta. I want to know how many degrees we're going to turn while we do that. Now notice the answer will probably be in radians. Well, it's going to come out of the math in radians. We could convert it to something else if we wanted to. I will accept it in whatever you want to do. I don't know why you would convert it to something else. It seems like extra work. And then we want to know the angular acceleration. Angular acceleration alpha equals what? Okay, I don't know if we have to go in the order that the problem asked in this. So a lot of times they'll kind of lead you on with certain questions. Okay, so here's with the order they ask. So I think it asked for the angular acceleration first. Let's just go ahead and aim for that. Okay, so what I want to point out here is that these particular variables, the ones that they were given to us, these are all linear. These are linear. This is linear. I guess time is linear or angular. However, if they give everything to you in linear, I'm going to suggest that when you go over here, you solve this problem linearly, okay? Meaning, okay, we know we're looking for an acceleration, and technically the acceleration that I'm looking for is this acceleration, right? But I don't see any reason to solve for that acceleration first because I was given a bunch of, initial linear velocities. So what I'm going to do is I'm going to solve for this, right? Once I have the linear acceleration, I can go up here, and I can get the angular acceleration here. Okay, the other option is to convert every single one of my linear velocities into angular velocities here and here and where, angular velocities. And once I have those, then I can solve for the the angular acceleration. I don't prefer to do it that way. Okay, so down here, what I'm going to do is I'm going to solve for the linear acceleration, so a sub t. Okay, so a sub t, if you remember your equations for linear kinematics, is the change in velocity tangential divided by time. Okay, now we don't usually put that delta down there, so we'll just call it like time. Okay, so we can call it delta t, it's fine. So a sub t equals the change in v sub t, so that's 95 meters per second minus 80 meters per second divided by the change in time, which was 10 seconds. Okay, so a sub t, we can do that in our head. That's 15 divided by 1, so that's 1.5 meters per second. Okay, now again, we've got the linear acceleration. And to get the angular, we just have to multiply or divide by r. We just have to figure out which one. So here's our equation up here. We've got a sub t equals r alpha. So we will go ahead and use that. So here we go. A sub t equals r alpha. Okay, so alpha equals a sub t over r. Okay, so alpha equals 1.5 meters per second divided by r. Sorry, meters per second squared. I guess I screwed that up here. Divided by r, which was 200 meters. So alpha equals whatever that is. Oh, I'm getting 7.5 times 10 to the minus 3. Again, notice the meters cancel out. So I'm getting per second squared. However, I know that this needs to be radians per second squared. Okay, again, remember it's a unitless unit, so you're gonna have to watch out for that. Okay, so there, we got alpha. Cool. All right, now what else do we need? We need one more. What else do we need? Oh, we need the angle the car moves through in this time. Okay, so let's go over here and let's look at our equations. We want delta theta. Okay, so delta theta shows up in several places. I could do it here, right? I know, well, I could get omega initial, omega final, and I could get, let's see, and I have alpha, so I could get it right here if I wanted to. However, again, linear equations, I was given this, I was given that. We've solved for this, so I can get to delta x pretty easily without having to convert everything into omega and omega naught, okay? So what I'm going to do is I'm going to solve for delta x, okay? And then once I have delta x, okay, I'm going to know that that delta x, that's the distance this car made it around that curve while he was accelerating from 80 to 95 meters per second to get up here. Okay, so that delta x is essentially the exact same thing as s. So once I have s, I can go up here and I can go, okay, cool, I got delta s. I'm going to do r, I know r, and that's how I'm going to get my delta theta. Okay, so let's go ahead and do it. All right, so down here, let's see. So I've got v squared, v sub t squared equals v naught t squared plus 2 alpha, dang gum, you alpha coming out of nowhere, 2a sub t delta x, okay? Now, again, because we're wrapping around that turn, we can just go ahead and call this delta s if we wanted to, and I guess I'll just go ahead and do that. Okay, so v sub t, again, let's see, what are we solving for here? Oh, we're solving for delta s. So delta s equals, if you trust my algebra skills, v sub t squared minus v naught sub t squared divided by 2a sub t. Okay, now remember we know a sub t because we solved for it right here, so that's going to just plug in. So if you trust my plug-in chug skills, just wait a sec. Okay, so we get 875 meters. So remember, you can think of that as delta x, but x in this case is kind of wrapping around a circle, so I'll just think of it as delta s. Okay, so again, remember if I want to go from, now that I've got a linear variable, I've got this, so I'm somewhere up here. I think that's not showing up. So I'm right here, so delta s equals r delta theta. So we'll go down here, and we'll say, okay, cool. Delta s equals r delta theta. So I'm going to solve for delta theta. Delta theta equals delta s over r. Okay, so delta theta equals, let's see, 875 meters divided by the radius, which was 200 meters. So delta theta is, I can almost do that in our heads, can't we? We can do that in our heads, can't we? Yeah, so that's going to be, let's see, so that's 4 and then 75 out of 200, so that's 4.375, right? Because that's 3/8. And notice the units are canceling, m over m. However, this is a delta theta, so that means we're coming out with radians, okay? So delta theta, we want 2 sig figs in this one, so it'll be 4.4 radians, okay? So there you go. So going 875 meters around the circle is equivalent to going 4.4 radians, or, that would be your angle through which you move. Okay, cool. So I hope that helps, and that should be about half of a class period. All right, see y'all.